How do we define heat capacity in the first place? What do we mean by the heat capacity of an object?
I believe it's defined as the amount of energy required to increase the temperature of a substance. So like energy over temperature?
Mostly yes, although there's one slight caveat to that. It's not just any amount of energy, it's specifically the amount of heat per unit of temperature. So let's say you modify a substance by adding some heat to it, and the result is that the temperature goes up. The heat capacity is the ratio of how much heat you added divided by how much the temperature changed as a result. And that's almost the same as change in energy over change in temperature. The difference is that change in energy could be heat or could be what else?
Work.
Right. That change in energy is heat and work. And this goes back to the conservation of energy, first law of thermodynamics. That the change in energy is heat plus work. So we're not quite defining the heat capacity as change in energy over change in temperature. We are more specifically defining it as just the heat divided by the change in temperature. Of course, if there's no work done, then it's the same thing. But if there is work, then those are not quite the same. And what would be a situation where there is no work done? Specifically, if we're talking about a gas in a container, how would you know that there's no work done?
Would it be constant volume?
Yeah, if we have constant volume, if we're dealing with an isochoric process, no change to volume, then there's no work. Because no change in volume, if the piston's not moving out or moving in, if nothing's moving, there's no work done. So an isochoric process, constant volume, guarantees that work is zero. So let's take a look at that situation first. If there's no work, so constant volume, isochoric, guarantees that work is zero. And if work is zero, then Q is delta U. Or what type of energy are we really talking about? We're talking about internal energy in general, but specifically what kind of energy is that here?
Thermal energy, if we're just talking about gases.
Exactly. If it's a gas the whole time, there's no phase change. So there's no bond energy, there's presumably no chemical reaction, so there's no delta E chemical, there's no nuclear fission or fusion, so we can ignore delta E nuclear or delta E atomic. We're just looking at changes in thermal energy. So we can make a substitution here. We can say that the heat is just delta E thermal. So the heat capacity at constant volume, which we denote by this subscript V here, is delta E thermal over delta temperature. So this idea of treating heat capacity as just change in energy over change in temperature, this is entirely valid as long as we're talking about constant volume process, as long as the heat is the only transfer of energy going on, no work. And this is basically how we were treating heat capacity at the beginning of the quarter. When we were thinking of delta E thermal as heat capacity times change in temperature, that works fine as long as we're talking about a constant volume process. And we have a formula for delta E thermal. In fact, we've got a wide variety of formulas for delta E thermal, but probably the most convenient one to be using is the microscopic formula we saw from the study of number of modes. The microscopic formula, the microscopic viewpoint of thermal energy. What was our formula for thermal energy involving number of modes?
1/2 times number of modes times KB times delta T. And that would be per particle, so you could also multiply it by the number of particles.
So this would be or I guess that should be delta E thermal, because we've got a delta temperature over here. So this is one way of writing out the total change in thermal energy. Change in temperature times 1/2 KB is the change in energy per mode, multiplied by number of modes per particle. And this is the change in energy per particle. But then we also multiply by number of particles to get the total change in thermal energy. Alternatively, what if we wanted to write this in terms of moles instead? How would you convert number of particles to number of moles?
You'd multiply by Avogadro's number and then the coefficient of number of moles.
Yeah, number of particles is just number of moles times Avogadro's number. So we can make this substitution. Number of particles can just be replaced by Avogadro's number times number of moles. So this is just another way of writing the number of particles. And some other convenient substitutions we can make. We have Boltzmann's constant and Avogadro's number multiplied together. What do those combine to?
R, the ideal gas coefficient or constant.
Yeah, exactly. That's just the ideal gas constant R. And then filling in the rest, we've got a delta temperature. We've got an N. We've got a number of modes. And we've got a 1/2. So this is a much more compact and often much more useful and perhaps even easier to remember formula for delta E thermal. So anytime you see delta E thermal, if it's convenient to do so, you can just replace it with this entirely. Number of modes over 2 times NR delta T. So let's try that. If we just replace delta E thermal with this formula, let's see what we get. So that's delta E thermal, then we have to divide that by delta T. And then what happens when we divide?
Delta T will cancel.
Yeah, the delta T's cancel out. And we're left with a nice neat formula for constant volume heat capacity. The heat capacity, if measured at constant volume, is just N times R times half the number of modes. So that tells you the heat capacity of any substance, any sample, as long as it's at constant volume. And heat capacity in general, I usually think of this as like a difficulty level. This heat over delta temperature, this is just describing how much heat it takes to change the temperature by 1 Kelvin, or whatever unit of temperature you're using. So a large heat capacity means it's very difficult to change the temperature. It takes a lot of heat to make a small change. Whereas a small heat capacity means it only takes a little bit of heat to make that same change. So this is just saying the more substance you have, the more difficult it is to change the temperature. And also the more modes per particle you have, the more difficult it is to change the temperature. Any questions on that so far? And note that this depends on how much of the substance there is. The more of the substance there is, of course, the higher the heat capacity is. But we often want to standardize this so that it only depends on the type of substance and not how much there is. So to standardize this, what's a convenient number of moles to use?
1.
Yeah, if we standardize this to 1 mole, standardize to exactly 1 mole, and we get 1 times R from the number of modes over 2. And so we call that the molar constant volume heat capacity, usually written as C, actually usually in lowercase c, C sub V n, or sometimes C sub V small. It's the molar, sometimes called the molar heat capacity or the molar specific heat. It is literally just the heat capacity of exactly 1 mole, standardized to a specific amount of the substance. So once you have this, you can calculate the molar specific heat of the type of substance. And then if you're dealing with, let's say, 5 moles of that substance, you just take this value and multiply by 5, or however many moles it is. And this means that the molar specific heat depends only on the number of modes. For example, let's say you've got a monoatomic gas. Any noble gas will work, let's say helium. For helium, how many modes are there per particle?
3.
3 modes, just the 3 translational modes, and that's it. So the constant volume molar specific heat for helium or any noble gas will just be 3 times R over 2. So for helium, I guess I should specify Cvm for helium or any noble gas. 3 over 2 is 1.5 R. And then R is about 8.3. 8.3 times 1.5 would be 12.15. And the units for R are joules per Kelvin mole. So the constant volume molar specific heat for helium or any noble gas should be pretty close to 12.15 joules per Kelvin mole. And if you look that up on a data table, it should be pretty close to that value. It's not necessarily going to be exactly that value because this derivation here is making some simplifying assumptions. We're assuming this is an ideal gas that might not be entirely valid in a real world scenario, but it should be pretty close. And so that should be a pretty good approximation for any noble gas, any monoatomic gas. Any questions on that so far?
That makes a lot of sense. Thank you.
Mm-hmm. Alternatively, let's say we were talking about, let's say a diatomic gas like nitrogen or oxygen, N2 or O2. How many modes would you expect for a diatomic gas?
It kind of depends on the temperature, but either 5 or 7.
Yeah, 5 if we're close to room temperature, 7 if we're a very hot temperature and we're activating the vibrational modes. Or if it's very cold, it might even be 3 if the rotational modes are frozen out. But 3 or 5 or 7, or it might even average out to somewhere in between those. But whatever temperature it's at, let's say you've got the rotational modes active, but the vibrational modes frozen out. You just have 5 modes. So 5 over 2 times R, 2.5 times R. That would be the constant volume molar specific heat for a diatomic gas. And note that that is going to increase if you raise the temperature so that the vibrational modes become active. So these molar specific heat can actually change if you raise the temperature high enough to activate more modes. But in a small range of temperatures, you can generally assume that it's going to be a constant value. It's only if you're changing the temperature enough to activate more modes or decreasing it enough to make some of the modes frozen out that that's going to change. Any other questions on the constant volume case so far?
So I was just wondering, for the graph that they give us, that's plotting the heat capacity, right? Not the specific heat.
If you're talking about exactly 1 mole of the substance, then heat capacity and specific heat are the same. Specific heat just means heat capacity standardized to 1 unit, either 1 kilogram or 1 mole. So we kind of interchangeably describe this as the molar specific heat or the molar heat capacity. They both mean the same thing.
Okay, so the relationship would be the same in that like both would increase as modes increase, right?
As the modes, yeah, as you get more modes, like let's say you're dealing with a sample of 5 moles of the substance. 5 moles is going to have a heat capacity that's just this value times 5 because of this times n here. But no matter how many moles you have or how few moles you have, that sample is going to have a higher heat capacity at higher temperature because you're activating more modes.
Okay, that makes sense. Thank you.
Mm-hmm. And of course, that only goes up to a certain point because, for instance, for a diatomic gas, the number of modes is going to increase up to 7. And at that point, they're all active. So you're not going to get more modes beyond that. Or for a monoatomic gas, for instance, it's going to be 3 modes and that's it, no matter what. Any other questions on this?
That makes sense.
All right, so that's constant volume. Let's take a look at the constant pressure case and see what changes. And for this, we're going to need to revisit the idea of the first law of thermodynamics, conservation of energy. So first law of thermodynamics again, delta U equals heat plus work. In this case, for constant volume, we were able to just ignore work entirely because if the volume isn't changing, nothing's moving, so no work is done. But in the constant pressure case, you are allowing the volume to change. You're just holding the pressure constant. So with the piston going outwards or inwards, work is being done. And how could we calculate how much work if it's a constant pressure system, but the volume is changing?
Could you just take the integral of the PV state diagram?
Yeah, if we go back to the pressure volume graph, if this had been constant volume, let's say it looked like this. Integral is the area under the curve, but if this is a vertical line, the area under the curve is 0, so no work at all. But for constant pressure instead, let's sketch that out. Let's say you have just one single value of pressure. Let's call that P naught, P sub 0. So you're going from some initial volume to some final volume. So you're going from initial to final while keeping the pressure constant. As you said, the work is just going to be the integral, the area under the curve. So if we take a look at the area under the curve, just drop a line straight down from initial, straight down to final. The area enclosed under the curve all the way down to the axis is the amount of work. And how would you calculate that amount of work in this particular case?
Would it just be the area under the line?
It should be that area, yeah. And since this is a rectangle, how would you calculate that area?
You would just do like the final minus the initial times the height.
Yeah, because that would, and we could abbreviate that as just delta V. And then the height is the pressure. So we could say work is the pressure, because that's the height. And note that that's not about change in pressure, that's just the pressure times the change in volume. So that's height times width of that rectangle. Also, one other thing we need, in this case, the volume is expanding. If the gas is expanding, are you doing work on the gas or is the gas doing work on you?
The gas would be doing work on the environment if it's expanding.
Yeah, the gas is expanding, so it's pushing out, the gas is pushing outwards on the surroundings. And I usually think of this as like if you've got a piston that can move vertically, it's a heavy piston, it's got some weight on it. As the gas expands, the gas is lifting that weight. So the gas is doing work to raise the potential energy of that piston. So a gas expanding means work is leaving the system. So we want to treat that as a negative number. This amount of work is a negative. Work is less than 0. But if the gas is expanding, delta V is positive. So what else do we need in this equation to make that work out? If we have a positive value for delta V, but we want work to be negative because work is leaving the system.
You could make the equation negative, so put a negative sign in front of the P delta V.
Exactly. A negative sign will balance that out. And this negative sign you should interpret as just meaning the opposite of. So the work done is going to have a sign that's opposite to the sign of delta V. For instance, if you're compressing the gas, delta V is negative, the gas is shrinking, but you're doing work on the gas to make it compress. So if delta V is negative, then work will be a positive number because the negatives cancel out. So that negative there is really just for directionality, to make sure that the sign on W is going to be correct. More generally, if the pressure is changing, you can still use this sort of setup, but instead of just a single value of pressure, the pressure might be changing. So more generally, we're going to use an integral to add up pressure times change in volume, still with a negative sign. So more generally, work is the negative integral of P dV. So it's still area under the curve, It still has this negative sign to account for directionality. If it's just a horizontal line, that works out to just this rectangle. So it's just negative P delta V. But more broadly, it's the integral. It's area under the curve. In this case, though, we can make that substitution. Work is just negative P delta V. And then we still have the delta U and the Q. So this is the modified first law of thermodynamics for the constant pressure. In other words, isobaric. If you have an isobaric process, this is the more specific first law of thermodynamics. And because we want to be able to write out Q over delta T, we should solve this for Q. If you isolate Q here, what do you get?
Delta U plus P delta V equals Q.
Exactly. We just add P delta V to both sides. And a very useful way to think of this, if you're adding heat to a system, like let's say you just got this gas in a container with a piston. If you add heat, you're going to make the gas get warmer. So that's an increase in thermal energy. Because that really is what this is. This is still delta E thermal. So if you add heat to the system, you are making the gas get hotter. You are raising the thermal energy. But what else happens to a gas with a piston as it gets hotter?
It expands.
Right, that's going to expand. So work is going to leave the system. So you could think of this as the heat added to the system minus the work leaving the system equals the change in thermal energy. Or by moving the P delta V to the other side, you could think of this as you're adding heat to the system. Some of that heat goes into raising the temperature. Some of that heat goes into expanding the volume. So that means if what you care about is raising the temperature, the constant pressure process is less efficient. You're going to have to add more heat to get the same change in temperature because some of the heat is wasted in raising the volume instead. Whereas for the constant volume process, all the heat you're adding goes directly into raising the temperature. But for the constant pressure process, only some of the heat goes into raising the temperature. The rest of the heat is used up in expanding the volume in the sense that work is leaving the system. So it's less efficient in the constant pressure system because some of the heat is lost in expanding the volume instead of raising the temperature. Any other questions on that so far?
No, that's making sense.
So let's go ahead and make that substitution. Wherever we see Q in the constant pressure process, we can replace it with delta E thermal plus P delta V. So let's do that. Constant pressure. In other words, isobaric. That means we can replace heat with not just delta E thermal, but delta E thermal plus P delta V. And let's see what that looks like. So
I have a quick side question. So in a isothermal process, when delta T is equal to 0, are you not able to have a heat capacity because you can't have?
Yeah, for isothermal, the idea of heat capacity doesn't really make sense because in isothermal, we're assuming delta temperature is 0. If delta temperature is 0, this equation kind of falls apart.
All right, cool, thank you.
I guess you could even consider the isothermal heat capacity to be infinite because you're adding heat, but you're not changing the temperature because work is leaving at the same rate you're adding heat. So mathematically, I guess we could say that the heat capacity is undefined or infinite for an isothermal system.
Okay, that makes sense. Thank you.
So isobaric, constant pressure, we make this substitution and we get heat capacity at constant pressure is all this divided by delta T. Delta E thermal plus P delta V, all divided by delta temperature. And because division distributes over addition, we can rewrite this as delta E thermal over delta T plus P delta V over delta T. So let's split that up. And now we can make some further substitutions. First term, we've got delta E thermal over delta temperature. Where else have you just seen delta E thermal over delta temperature?
CV.
Yeah, that's just CV. So since CV is delta E thermal over delta temperature, we can make this substitution here. We can say that constant pressure heat capacity is constant volume heat capacity plus this extra term. And this is a very important result in its own right. This is saying that the heat capacity at constant pressure will be the heat capacity at constant volume plus a little bit extra. And again, this goes back to the idea that heat capacity is the level of difficulty. Large heat capacity means it takes lots of heat to change the temperature a certain amount. Constant volume heat capacity means if it's constant volume, it takes a certain amount of temperature, a certain amount of heat per degree Celsius of change. The constant pressure heat capacity being larger, constant volume plus a little bit extra, means that at constant pressure, it's more difficult to change the temperature. Again, going back to the idea that at constant pressure, only some of the heat goes into changing the temperature. The rest of the heat is used up in expanding the volume. So it's more difficult to change the temperature if you're at constant volume. Sorry, if you're at constant pressure, because you're expanding the volume as well as changing the temperature.
Is there a way to standardize CP to like similar to how you did it with the constant volume to 1 mole?
Yes. Yeah, we are going to be standardizing this by assuming it's exactly 1 mole. But there's one other thing we can do to simplify first before we even do that. And that is messing around with this fraction of P delta V and delta T. Because what other formula, what other equation relates P, V, and T together?
Ideal gas law.
Yeah, we are talking about a gas, so we can invoke the ideal gas law to make one more useful substitution. So going back to the ideal gas law, we know that pressure times volume equals N times R times delta times T. If we apply a delta to both sides of this, because we are talking about changes here, delta P times V equals delta nRT. But on the left side, what's the only thing that's changing in this particular process?
The volume.
Right. Volume is changing. We're assuming pressure is constant because it's isobaric. Since pressure is constant, we can pull that out of the delta and get P delta V. And also here, what's the only thing that's changing?
Temperature.
Right. And an R are constant, so we can pull those out of the delta. And we just get P delta V, which is exactly what we have in the numerator, is the same as NR delta T. So we can make that substitution. P delta V, because of the ideal gas law, can be just replaced completely with NR delta T. And we're still dividing that by delta T, of course, because that's part of the definition of heat capacity. So when we divide those, what happens?
The delta T's cancel and you're left with just NR.
Exactly. So that's the little bit extra. I mentioned earlier that the heat capacity at constant pressure is the heat capacity at constant volume plus a little bit extra. We now know exactly what that little bit extra is. So that means in general, the heat capacity at constant pressure is exactly the heat capacity at constant volume plus this extra term NR. So that's the little bit extra. That's the difference between CP versus CV. And sorry, go ahead.
So the specific heat at a constant pressure is dependent on the number of moles per particle as well as the moles.
Yeah, if we're talking about an arbitrarily sized sample. But you mentioned standardizing earlier. What would be a good number of moles to standardize it to?
1.
Yeah, so once again, let's standardize this to exactly 1 mole. If we say we have exactly 1 mole just to standardize it. Then instead of saying the constant pressure heat capacity, we're going to say the constant pressure molar specific heat, little c sub Pm, or little c sub P mole. And likewise, since we're standardizing this to 1 mole, CV is going to be CVN, the molar constant volume heat capacity, or specific heat. And then N times R becomes 1 times R, so that's just R. So this describes how these quantities are related. The constant volume molar heat capacity is going to be R times number of moles over 2. The constant pressure molar heat capacity is going to be that much plus 8.31 plus R. So R is that little bit extra if we're standardizing it to exactly 1 mole. In fact, we could even make this substitution as well. We could say Cpm equals, if we actually fill this in, R times number of modes over 2 plus an extra R. And a very convenient thing we could do algebraically also, if we factor out an R over 2, and just for consistency, I'm going to write this as times 2 over 2, so we have the same denominator. If we factor out R over 2, what's left?
Modes plus 2R.
Yeah. Or just plus 2, because we're factoring.
Just 2.
And that's almost the same as what we had here, R over 2 times number of modes versus R over 2 times number of modes plus 2. So in a way, mathematically, you can say that constant pressure instead of constant volume just makes it act like it has an extra 2 modes.
Huh, that's kind of wild.
Yeah, it's really neat to see how these quantities relate together. That just starting from this definition, plus a whole bunch of substitutions, we get these 2 very convenient interlocked formulas for what happens if the volume's constant versus what happens if the pressure's constant. And you can, of course, calculate either one of these as long as you have the number of modes. Like again, if you're talking about, let's say, diatomic molecule or diatomic gas with the 5 modes active near room temperature, constant volume heat capacity would be 5 over 2 times R. Constant pressure molar heat capacity would be 7 over 2 times R. And which one of those you would actually use in terms of comparing heat added versus temperature change depends on how you're running the experiment. If you're keeping the gas at constant volume but allowing the pressure to change, you'd use Cpm. If you're keeping the gas at constant volume but allowing the pressure to change, you'd use Cvm. And if both are changing, then the actual heat capacity is going to be somewhere between these. But these are the 2 standardized extremes. This is basically the lowest the heat capacity can be. This is the highest the heat capacity can be. And then any other process that mixes the pressure and volume is going to be somewhere between those.
So CVM is the lowest heat capacity, or CV?
This one's going to be the higher one because it's the lower one plus an extra R.
Okay, all right, yeah.
Any other questions on that so far? And let me get a picture of this chart while I've got it on the screen. Any other questions on heat capacity or the thermal energy stuff in general, or do you want to try out some of this stuff on microstates and entropy?
Let's do some entropy.
Okay. So what are you working on entropy so far? Any specific questions or examples on that you'd like to work on?
I think for me, I kind of just would like a general overview of it.
The microstates idea?
Yeah, microstates, yeah.
Okay.
And like the probability stuff.
Yeah.
I'm definitely like not great at statistics, so it's a little weird for me.
Then let's take a look at that. Any particular random events you want to focus on, like coin tosses or drawing from a deck of cards or rolling dice or something like that?
Can you do one that has more than two possible options? Like I know the coins, where like there's only like heads or tails.
Yeah. And then, I mean, that's really the main reason why the early focus is often on coin tosses, because it's such a simple case, because there's only two possibilities. You can explore a lot of the results, a lot of the terminology and some of the equations and stuff with a simple introduction. But the simplicity kind of falls apart when you look at more complicated cases. Let's take a look at an idea I often find useful is if you've got several containers and objects that can be in any of those containers. Like let's say you've got half an egg carton. So you've just got 6 locations where something can be. Six places. And let's say we put, let's say 4 marbles into this. So we've got 4 marbles, and in order to be able to tell them apart, let's say there are 4 different colors. So we've got like, well, let's say red, orange, green, and purple marbles. Each one of those marbles could be in any one of these 6 locations. And let's assume that the marbles are small enough that hypothetically all 4 of them could be in the same place. All 4 of them could be in the same bucket here. So you might have, for instance, let's actually label it. Let's say we have locations A, B, C, D, E, and F. So maybe all 4 marbles are in the same location. Maybe all 4 marbles land in place D. Or maybe they all land in different locations. Maybe you get the red marble in place F, the orange marble in place A, the green marble in place E, and the purple marble in place C. Each one of those possible arrangements would be a microstate, because a microstate is talking about a specific listing of what's going on with each piece of the system. So microstates here so each microstate, should specify each microstate is a listing of the location of each marble. And we could just assume an order for the marbles. So let's say the order is, this, let's say red, orange, green, and purple. So you got 4 marbles, and a microstate would just be listing where's the red marble, where's the orange marble, where's the green marble, where's the purple marble. So some examples of these might be, let's say, F, A, E, E. This listing would just mean the red marble is in place F, the orange marble is in place A, green marble is in place E, purple marble is also in place E. So this would be an example of a microstate. Or maybe they're all in location B. This would also be an example of a microstate, where red marble is in location B, orange marble is in location B, and the green marble and the purple marble, they're all in location B. So there's lots and lots of microstates. A microstate would just be a description of the location of every marble. Any questions on that so far? And sorry, go ahead.
Oh no, I just don't have any questions.
Okay. And then a state, or sometimes called a macro state, is more of a big picture description of the whole system, usually not listing out the specifics of each marble. So for instance, if we said like, if we said all the marbles are in the same place, this would be an example of a state. Or maybe we could say all the marbles are in different places. Or we could say at least one marble is in place D. Those would all be examples of states. And you can get very, very imaginative with states. You might say like, all the marbles are in the lower half of the carton, or half of the marbles are in the upper half, half of them are in the lower half, or there's no marbles in place B. So there's many different ways to describe states, however you want to describe just a broad general picture of the whole system. But the important thing is each state is associated with some number of microstates. For example, all the marbles are in the same place. What would be an example of a microstate that corresponds to all the marbles are in the same place?
You could have like the B example, but you could have that for any of the 6 boxes.
Right. So B, or A, or C, all the way up to F. So this would be the list of all of the microstates that are associated with this state. That's 6 microstates. So we would say omega equals 6, omega being the number of microstates. And the number of microstates determines how likely that result is. There's only 6 ways that this macrostate can happen. So if you just put the marbles in the box, close the lid, shake it up, and then open it up again, because there's only 6 ways this can happen, that's presumably going to be very unlikely. And specifically to calculate probability, we know how many ways there are for this outcome to happen. How would we turn that into a probability?
You'd have to find the total number of microstates, and you could divide. Exactly.
Because we're assuming here that each microstate is equally likely. FAEE is exactly as likely as BBBB, which is exactly as likely as CCCC, and so on. So that means the probability depends entirely on how many microstates are associated with that outcome as a fraction of the total number of microstates. In general, probability of some outcome equals number of microstates for that outcome divided by the total number of possible microstates. So how would we figure out the total number of possible microstates here?
So you have 6 different options.
Mm-hmm.
So could it be like 6 to the however many number of events?
Yeah, because you could think of the location of each marble could be thought of as an event. If you just imagine tossing in these marbles one at a time, the first marble could be in any of these 6 places. The second marble could be in any of these 6 places, because we're assuming that the marbles don't fill up the holes, that each hole could fit possibly all of them. The third marble could be in any of these 6 places, and the fourth marble could be any of these 6 places. So each marble is an event in the terminology usually used in probability theory. There's 4 separate events that are completely independent. They don't influence each other at all. which means we should be able to just multiply those numbers of outcomes together. 6 times 6 times 6 times 6. So that would be omega total, the total number of possible microstates. And we know there's 6 microstates associated with this outcome. So the probability of all in the same place would be 6 out of 6 to the 4, which reduces to just 1 over 6 to the 3rd, which is, I think that's 216. Yeah. 1 out of 216 is a pretty low probability. So assuming that they all end up in the same place, very unlikely. Any other questions on that?
I just had a question. So one of our quiz problems, it was kind of a similar question, but we had to like add all of the microstates rather than multiplying the probability. It was like 1 out of 100, and then we had to like multiply it by 4. So how do we know like when it should be like multiplied versus added? Is it just like independent versus dependent events?
It's usually more about and versus or. In this case, we're talking about like the red marble lands in place F, and the orange marble lands in place E, and the blue marble or green marble lands in place E, and the purple marble lands in place E. In general, and means you're going to be multiplying. If you're talking about or, it's going to be adding. So for instance, if we wanted to know, for example, the probability that the first marble lands in place A or the second marble lands in place A, we would be adding those together instead of multiplying.
Okay, that makes sense. And I also just wanted to ask, do you have any like recommendations or like tips for like preparing for the final, or like what we should focus on the most?
Is the final going to be cumulative, like covering everything from the whole quarter?
They said it would be cumulative, but more focused on stuff that's been like more recent.
Yeah, that makes sense. I think I would try focusing on connections then. Like take a brief look at all the topics, but try focusing on the connections between them. Like go back and look at the early stuff on conservation of energy from the perspective of what you've learned since then. And ask yourself, like, how does this conservation of energy idea connect to the new stuff in thermodynamics, the new stuff about entropy? Because this is all connected. We're really just looking at one big overall topic with a lot of individual details. And try out examples, even take a look at some of the examples from homeworks earlier in the quarter and ask yourself, are there other ways you could do this based on what you know now? Or other ways you could approach these problems? So look for those connections.
Okay.
And I also have 1 or 2 practice finals on the website as well. If you go to math.ncheese.org/P7A, I've got, I think, a practice final and also 1 or 2 other worksheets with solutions worked out as well. So take a look at those, give those a try, and let me know if you have any questions about those too.
Okay, I'll definitely take a look. Thank you.
Good. You're welcome. See you next time.